Oh, hi. I'm at Matthews A, the lecture theater, and the display is not showing the browser. I'm using Chrome. Is Chrome okay, or I have to use some other browsers? Yep, I'm using the internal. Yep, internal. Yeah, on the projector, it is showing just the blank screen with the bottom bar, but it doesn't show the browser, the Adobe Acrobat and anything else. Yep. A. A. Mm-hmm. Yeah. Okay. No, the projector is still blank with just the bar at the bottom. Yeah. Bottom left, yes. Shall I press that? Hold that and what? What's the other one? Little people, Peter. Yep. Yeah. Yep. Yep. Shall I duplicate? Something is happening. Yep. We are in business. Okay. Thank you very much. Thanks. Okay. Bye-bye. Sorry for the technical glitch. We are back. So welcome to the last lecture of week 2. Just to remind you that we are heading towards a long weekend. Monday is closed, so there will be no in-person lecture on Monday because the university is closed. What I promised, as you have noticed in the course outline, is I'll record the lecture and release the lecture for Monday only online. So when you go to week 3 lecture, you will see the recorded lecture for Monday. Thursday, we'll be back here. Okay, so that's the lecture. For the lab, we have decided to offer online lab on Tuesday at the same time to all those affected students. So all the affected students will receive an email. You will be contacted regarding the online lab, so nothing will be missed. Today we are going to continue with HTTP. This is the application that we started with last time, but today we'll try to finish it. Just to give you a context, there are many applications in the computer networking in the internet, as you know. But HTTP supports the web services, the web browsing, web hosting, and all sorts of web-related things, which is very, very important because, as you know, it's very difficult to have a business without online presence. And to have online presence, you need your web services, right? Web hosting, and then millions of customers from all over the world can access your business, they can pay for it, they can select the products, and all sorts of things. The underlying protocol, the computer networking application layer protocol that supports that is called HTTP, Hypertext Transfer Protocol. What I also would like to remind you, every lecture, I think we should remind ourselves is that everything is protocol stack, if you recall. So you have 5 layers, right? 1, 2, 3, 4, 5. This is the application layer. So this is application layer, and this is the transport layer. So if you recall, I said last time that the transport and the application, they are tightly coupled, because if you're writing an application code, then you have to make a decision which transport services you want for your application. So if you look at HTTP, this is an application. So if you want to write code for HTTP, then you will see that you need services of TCP. TCP stands for Transmission Control Protocol. We have discussed at length, I think in one of the lectures, I think lecture 1, TCP versus UDP. So TCP provides a reliable service, and HTTP makes use of TCP. So you cannot run it on UDP, right? TCP will be covered in details in one of the subsequent lectures, maybe lecture 5 or 6 after the break. But today we'll be referring to TCP very briefly, just saying that you need a TCP socket, you need a TCP connection and things like that. One thing to remember for you is that TCP is connection oriented. It means that anything you want to transmit over TCP, you have to set up a TCP connection. The reason is that it's very reliable. So if you want to guarantee that every single byte you transmit will be received by the other end, you have to make sure that it's a connection oriented, so you can maintain the states. You know that what's the sequence number of the last packet. If it was not received, you can retransmit and things like that. So you will hear me referring to TCP connections a lot, and that will significantly affect the analysis that we are going to do today on the performance of HTTP and what sort of protocols are available to improve the performance. Okay, so HTTP, just like any other applications, is based on client-server, right? So client-server is the fundamental paradigm. So as you can see, if you are running a web browser, such as Firefox, Chrome, or in your phone you are running Safari, for example, if it's iPhone, then these are like browsers. These are clients, right? So clients need a server. So if you're writing HTTP, you have to write 2 pieces of code. One is for mobile devices, such as smartphones, browsers, and one is for the server. So which one will be running 24/7, the server or the client? Server, yes. So the codes are slightly different, and as I said, you will learn them in the lab, and in the assignment you have to implement them. But here, as you can see, if you are running HTTP, then you have to run a server code in a server somewhere in the internet, and the clients will run the browser, which is the client, and they send the HTTP request for an object. We'll talk about the object. And the job of the server is basically to deliver that object to the client. It's as simple as that. Your website might look very pretty with beautiful videos, voice, text, pictures. But at the end of the day, the protocol that supports that beautiful user interface is based on this simple protocol. It requests an object, and the server's job is to deliver that object to the client. Nothing more, nothing less. So we have to learn what is an object, how you can fetch that object, how TCP comes into play, and how TCP influences the experience of the user in terms of delay in getting the object. What can we do to improve this experience? How do we compare them? How do we analyze them? If I give you a case study, can you tell me which one is better? And how to find out how many seconds it's going to take given this case study, and things like that. So today's lecture is full of that. We would also like to finish another one, email, right? Email is another example application, but we'll only do the overview kind of for email. So HTTP will be our main part of today's lecture. We'll go deeper into HTTP, and if you like the questions in the midterm exam, will be more based basically on these HTTP constructs that we cover today. So pay attention. They involve some small maths, not really big maths. But if you have any questions, just let me know, okay? Yeah. Oh, sorry. Okay, so without further ado, let's delve into the details of HTTP. Just wanted to say that HTTP uses TCP, and TCP is stateful, but HTTP is not. And in terms of terminologies, like what is stateful? State means that you need a connection, and you maintain this connection, and what happened previously is important for what you are doing now. So you are maintaining the states of the past to make the decisions for present, right? HTTP is stateless because it relies on TCP, and TCP is stateful. So TCP is very complex. Any protocol that you write which is stateful, which needs to maintain the states of every transaction, every transmission, is very complex because it has to maintain the state. It needs to know what happened previously. And that's why it's better to, for efficiency purposes, we try to be stateless. So HTTP is stateless, but it makes use of TCP at the bottom, so it doesn't worry about reliability. TCP will take care of that. Okay, so you can read all of these things. It's a very straightforward. The important thing that I want to go into is the performance, okay? Because if you're writing a code for your HTTP, if you are making a decision, if you are the analyst for the company, and you are trying to host this website, right? So you have to make few decisions, like what sort of protocols are useful. So in the internet, there are many standards, right? And the standards are evolving. So the simplest one was 1.0, and then they are moving into 1.1, 2.0, and things like that. So what are the fundamentals in terms of performance? What is the performance, first of all? So who can tell me what's the main performance metric for HTTP or any web should be?
Page load time?
Yeah, page load time. So you click and then you wait, right? This is web. You like something, you click, and ideally you would like to see instantly, but instantly doesn't happen because it's a huge network of networks, and the object that you are looking for may be very far, stored somewhere, far away from you. So it's not just the distance when I say far, there's also protocol implications, and that's where we are coming in. Interestingly, it's not really the distance, because distance is propagation delay, and it is handled by the speed of light. So unless you increase the distance by thousands and thousands of kilometers, speed of light is pretty good, right? If it's 100 kilometers, it's not a problem, right? And web hosting, you will see later, I'll mention, there are big industries now. They replicate the web servers. So whenever you hit something you like, it usually comes from somewhere closest to you. So it's not the propagation delay that's the bottleneck. So your experience, page loading time, is bottlenecked by interesting interferences by this TCP and HTTP. Because HTTP cannot do its job on its own. It needs the services of TCP. And that's what I'm going to explain to you. What is this interference? What is this interaction between TCP and HTTP that creates this bottleneck in page loading time? And what can we do to improve it? Is there any standard solutions? and what are the fundamentals behind those protocols. So there are many factors, as I told you. What we will focus on is the protocols, is the TCP and the HTTP interaction. That's where we'll focus. Network bandwidth is something I will show you that can solve the problem at a cost, because network bandwidth means you have to pay for a link which is 10 times has 10 times higher speed than the previous one, for example. And as you know, if you want higher speed links for your network connection, you have to switch to a higher cost plan, right? So it's expensive. And I will show you later, despite it being expensive, it's not the most effective solution, right? Because the bottleneck is still in the protocol, and that's why we want to focus there. And then we talked about RTT. First of all, what is RTT? So RTT, who can tell me this acronym? It's full of acronyms at the back. Round trip time, yes, return trip time. It's called round trip, okay? So you send something one way, and then the object comes back. It's the round trip, right? So everything is round trip. And this round trip time, as I told you, is like the propagation delay, right? It's the distance, and still you will see later that these are not main contributing factors, although they are, and we will focus on protocols. Page content structure, we'll also talk about that. Okay, so if you look at the business model, right? So we are here because internet is very popular at the moment, and many businesses, millions and millions of businesses are making use of the internet to make money, to deliver and attract customers online. So if you look at the business model, then you see there are three entities who want to benefit from HTTP. The first one is the user. Like us, we would try to find things in Amazon and everywhere, and browse the website of the university or Wikipedia and things like that, right? So we want fast downloads, we want high availability. Sometimes the Google servers are down, and if it's down for a few seconds, like we are inconvenient users, but if users are inconvenient, then like the businesses are also losing money, right? So availability is important. If you're the content provider, for example, Netflix, you have to use HTTP, as I told you, that now they are moving into HTTP server to deliver the video. HTTP was designed for text and images, but they are using it for video. So content providers, they want cost-effective, happy users, and they want infrastructure to be cost-effective. And as you can see, if you improve the protocol, HTTP, which will be the focus of today's lecture, then you can achieve faster downloads. And we'll show you how much faster it can become by adopting some of the protocol improvements standardized today. We'll also talk about caching and replication, okay? And you'll see that by implementing caching and replication, you can improve the user experience. You can also improve the network overload. So when we say network is an entity, network is the networks of networks, the internet, and this is not really owned by any particular entity, the entire internet. But if the internet is congested and overloaded, then everyone will suffer. So the standards that are coming out of IETF, RFCs, they are for the entire internet, right? These protocols are implemented by anyone who is connected to the internet, and they contribute to the traffic and congestion in the internet, right? So the standard, when they make the standard, they also try to maintain this network so that it doesn't get overloaded. Because if it is overloaded, then everyone suffers. So these are like few dynamics. So if you look at solutions, the protocol improvements, caching and replication, and I will explain them later. They are all kind of solutions, and I'll also talk about the bandwidth improvement as another solution and compare them, how all of these solutions compare to the main solution, which is the improvement in the protocol. Okay. So, I would like to introduce two terminologies, non-persistent and persistent, right? So these are just terminologies, but I will explain why they are so important and what do we mean by persistent and what we mean by non-persistent, right? So both of these terminologies are arising from these interactions with the TCP, the transport layer at the below HTTP. HTTP on its own cannot go and fetch an object. It can request for an object, right? But, okay, first of all, what is an object? So, in web browsing, object can be text, a piece of information, text. It can be an image, like JPEG or any other BMP, whatever. It can be a video even, right? That's also an object. All of these things, all of these objects are basically stored as files in the operating system of the server. So when you request an object, it's basically the transfer of the data in the file, right? And you want it to be lossless. You don't want, because the object needs to be brought into your browser before you can use the object, okay? So it means it requires 100% reliability. You cannot afford to lose a single byte of that object. Otherwise, this object transfer is considered invalid and you have to restart. That's why we are using TCP, right? So if HTTP cannot on its own achieve 100% reliability, it has to use the services of TCP. So if you look at TCP, TCP is connection oriented. So you have to set up a TCP connection, right? And the TCP connection setup is something we are not going to explain today. We'll leave it to that lecture when we explain TCP, but I'll just tell you one thing, is that TCP is complicated protocol and it experiences one round trip time to establish the connection. That's all you need to know today. Okay. One round trip time to establish the TCP connection. Why I'm referring to one round trip time? Because the experience, the performance metric is the page download time, which we will measure in seconds or in terms of round trip time, in terms of time. So one round trip time gone just to set up a TCP connection, and I'm going to use this picture here to explain, and you can read the text. So one round trip time is gone, right? Just to establish the TCP connection before HTTP can request a file. So now HTTP is requesting the file, and the file will be transmitted here. So one RTT for the TCP, one RTT to get the file, right? And little bit of delay here, depending on the size of the file. You know that the bits are transmitted sequentially, so if the file has 1,000 bytes, you have to send bit by bit, right? So there is a slight delay. It's called the transmission time, right? We have already seen the definition of the transmission time in the context of a packet. Here is in the context of the file. So you have to add that up, because if the file is big, then the transmission time will be significant. But as you can see in this picture, it's very small because this is just the initial file. So I'm quickly coming to this formula. I don't want you to memorize this formula, but I want you to understand how we derive this formula. So it's up to you. You can just use the formula to quickly get the answer, but then you have to be very careful. Am I using the right formula for this question? Right? But if you understand how I derive this formula, then no matter what the question is, you can derive your page loading time for that particular case study. So let's do this formula. Let's see how we get this. Okay, so one thing I have not done yet is to explain what is non-persistent, right? But then I have to explain what is persistent, right? Now, TCP, if you open a connection, at some point you have to close the connection, right? You can't leave the connection open forever. So, the first protocol, HTTP, which is 1.0, says, it's very simple. So if you want to get an object, open the TCP connection, get the object, close the TCP connection. Because you don't want any TCP connection hanging over the HTTP. It's a management overhead for the server, for the client. So just close the TCP connection. You want to get another object, open another TCP connection, get the object, close the TCP connection. So it's very simple protocol. It was very successful, widely deployed. Even today, as we speak, there are many servers and many browsers which support this non-persistent HTTP 1.0. Right? It's getting obsolete. I'll show you what's the problem with this in terms of performance. But in terms of overhead, this is the simplest software that you can write. And sometimes we ask our students to write this software as assignment. This particular assignment, there will be something else. I'll talk about the assignment later. What is persistent and what is non-persistent? So if my TCP connection, okay, so the next thing we need to know, and I have to ask you, how many objects you think you have in a web page? So when you are just browsing a web page, how many objects do you see? One? No. More than one? Yes. It can be 10, right? It can be 20. Can it be like 100? Yes. There are some pretty web pages where there are so many things, and everything is clickable. Some videos, some sound, some beautiful pictures, some more information. Click here to get this and that. Right? So, if I use this simplest one, then I have to open a TCP connection, get that object, and then display it, close the TCP connection. I have to get another object. So before I do this page, I have to open and close many TCP connections just for one nice page, right? It means this TCP connection is not persistent for this page. It didn't persist. I had to close it, and then I opened another TCP connection. Persistent means until I finish downloading every object in my page and display the nice page, my TCP connection will not close. It's a persistent TCP connection which will remain open until I download all the objects of my page. So that's the difference between persistent and non-persistent HTTP. Okay? We'll start with non-persistent because the simple one. We'll try to derive the formula for the page load time, try to justify this formula so that you understand how we derive it. Then we move to the persistent, and when we go to persistent, you will see there are other options to improve. So it's just drag on, and we have 2 hours, so that's fine. That's the focus. So you can see one TCP connection for this and one TCP connection to get the object plus transmission time. So this is for every object, right? So for every object that you want to download, you have this problem. I mean, you have this time that you have to experience. So if you have 10, then you have to multiply this with 10, right? Okay? So sometimes I'll just draw a picture to show you these two different scenarios. So this is your browser, right? This is your browser. And this is the server, right? So you say, okay, request and response. You try to request an object, you get the object. So all these objects may be in the same server, right? So even if all the objects are residing on the same server, you have to open the TCP connection, close the TCP connection, open the TCP connection, close the TCP connection. Sometimes these objects are spread over multiple servers. So again, this is another server. There are some objects. So you have to get some objects from here, some objects from there. So that's what is saying, that multiple TCP connection setups to even the same server. Or if the objects are in different server, still you have to get them sequentially and open and close the TCP connections. So that's HTTP 1.0 is very successful because of its simplicity, because it doesn't persist the TCP connection. Okay? Now you might be wondering if the objects are, I already know, I download the index file. So I'll explain what is the index file. Index file or the base file is the first web page, HTML 5.0 or whatever, which is the base file. Once you get the base file, you basically know how many objects are there, where they are, and how many of them. So why don't I, in parallel, so now we are talking about parallel TCP connections, right? Why don't we do that? So this is another question we have to answer, right? So what I mean by parallel, so you can see, let's say that I have two servers, right? So this is server 1 and this is server 2, right? And this is my browser client. And it downloads the HTML base file and it says that there are two objects in this HTML file. Object 1 is residing in server 1, object 2 is residing in server 2. So the question is concurrent, or you can also say parallel, right? Okay? So this is TCP connection 1, right? TCP 1. And you can say I can open another TCP connection, which is TCP 2. So this is parallel. You open both TCP connections at the same time to two different servers. This is concurrent. And you might say, oh, if I do that, I can get these two objects at the same time. Parallel processing. We know that the parallel processing speeds things up. The question is, why don't we do that, right? So that's what we are asking here. Why don't we do that? Who can tell me why we are not doing parallel TCP downloads at the moment? Most of the browsers in the internet are not doing it. Why? Who wants to answer this question? Do you want the microphone? Yeah, so we have.
The sequential order of objects is not maintained.
Okay. So the answer is sequence order is not maintained. Why is it important for me to maintain the sequence?
Because we need certain objects before the other objects.
Okay. All right. I buy it to an extent that sometimes you need some objects to be drawn before you want to see the other objects. Yes. Yeah. So yeah, this is not a bad answer. But in many cases, sequence is not important, right? As soon as you get all the objects, you are happy. So if it speeds up. So can someone else tell me why the parallel processing is not used in the practical systems, despite its huge benefit? Just interested in your opinions. I'll give you the answer.
Because it's sharing the bandwidth
Sharing the bandwidth?
between the connection. Parallel.
Okay, so if you have lots of bandwidth, if the bandwidth is not used, I'm trying to go to the answer that I was trying to explain, but all of these are correct, kind of.
I just had a question. The parallel HTTP connections, when you say HTTP connections, HTTP is non-persistent, so is that just the underlying TCP connection?
Parallel TCP connections. Yeah.
Yep.
It is the parallel TCP and HTTP is similar. So if you open another TCP connection, you can request an object from that one as well. So your HTTP is also parallel.
Yeah.
So the question is why we are not doing it. I think you didn't give the answer. You asked a question, right? Yeah. Okay. Does anyone have the answer? You have the answer now? Okay.
So it is possible that multiple devices are trying to connect to the same server, so it can lead to the failure of the server, or it can lead to the failure.
You are nearly there. This is nearly the perfect answer. I'll show you what he's trying to say. So I can write a lot of things in the answer, but let me draw what you are trying to say, and you'll see that if this is a server, right? So this is browser, and this is a browser, right? This is a browser. So if this browser opens, multiple TCP connections, then every browser opens multiple TCP connections. Then quickly you see that you are overloading a server because there are hundreds and thousands of clients trying to access the web pages from your server, and instead of one TCP connection at a time, they are opening hundreds of TCP connections at a time. There's a server load to maintain the total number of TCP connections at a time explodes, and that becomes a huge server overload. So if I am running a server, I wouldn't like it. Yep.
Can I ask, what if you have multiple servers? Just you do one connection for each server?
Yes. So at the end of the day, this is again will translate because there are huge infinite population of the clients, right? So they go to many servers, everyone go to many servers, so at the end the server load will increase. So at any one time. So the rate of TCP connections that I am opening up as a client, I'm increasing, right? Instead of one at a time, I'm doing 100 at a time. So whether it's in the same server or distributed over multiple servers, at the end of the day, and an aggregate, all the servers will receive 100x more load in maintaining the TCP connections. And when we study TCP connections, you will see what a pain it is to maintain the TCP connection, because there are so many states for a TCP connection. So all the memories and all the CPU time goes into just maintaining the TCP connections. And it's also denial of service attacks easy to launch. Ask the TCP connection. We'll talk about these things when we study TCP. Here, we say that the load explodes if you try to open too many TCP connections. And in the internet, this is very important because if the servers are overloaded, then your page loading time bottleneck would shift to the server overload problem, the server response time, right? You ask for an object and the server has the object, but the server cannot just deliver it in time because it's overloaded with lots of TCP connections. So it's not an easy solution to just go and do the parallel. The reason I mentioned is because in the rest of the lecture, I will not explain the parallel more, but I will switch to another solution that can I just use the sequential, I mean not parallel, but still improve it. What can I do? Right? So that leads me to persistent. Okay, so this is not parallel, but instead of closing the TCP connection, I still have one TCP connection. I'm not asking the server to open 100 TCP connections. But the TCP connection that I open for my page download, I will not close it for one object. I will keep it open for all the object download from your server, right? So multiple objects will be transmitted over the same TCP connection over time. What's the benefit? Exactly. So remember, one round trip time to open a TCP connection. You are now amortizing this cost over multiple objects. So if you have 100 objects, it's one round trip time over 100 object downloads. But before, it was 100 round trip time overhead. So the savings is immediate and scales very well once you have complicated web pages. And that's why persistent TCP is the state of the art. So in the internet, when you are using any Firefox, Google Chrome, Safari, the chances are it's using persistent. And the savings are enormous, and I'll show you through formulas, I'll show you through actual numbers, and we'll have a quiz. Okay, you can read all of these things, but I think you got the idea, right? What I want to show you that in persistent, there are two ways to do persistent. One is pipelining, and one is not pipelining, right? And they will also affect your experience, the delay time. So we'll start with pipelining. Okay. What is pipelining? By the way, so it's 1.1. So 1.1 replaces 1.0. So there are more servers running 1.1 now in the internet than 1.0. Right. So what is pipelining? So let's say I have 3 objects. In this case, there are 3 objects, right? What you can see in the picture is that not only you are using the single TCP connection to download these 3 objects, you are requesting to download these 3 objects straight away back to back. You are not waiting for the first object to be downloaded first before you request the second object. This is pipelining. You just send all your requests because once you download the index file, the base file, you know all the objects in your web page. So pipelining means just request all of them at the same time. So let's follow the timeline. So this is the famous timeline you will see over and over again in computer networking. The vertical downward is the time axis, and the horizontal is the protocol messages, right? It's a convenient way to capture both the protocol and the timing relationship, right? So you can see you open the TCP connection, one RTT only, then you request the file. So when I say request the file, what do I exactly mean? And some students will ask in the forum, I'm sure. So let me just tell you. So when I say file, I'm referring to the base, or sometimes it's called index file. That's what it's an HTML. Okay. So that takes one RTT. You now, at this point of time, you know that you have 3 objects, right? So see all the requests for the objects. You request object 1, then you request object 2, and this you request object 3, back to back without waiting for the first object to be downloaded. And when you receive the first object, it transmits the first object, transmits the second object. So this is pipelining, right? So pipelining is happening here. So this pipelining is happening here. So is that clear, the pipelining? And non-pipelining means you get one object, then once the object has been downloaded, then you request for the second object over the same TCP. So you do not have the TCP opening overhead, but it will be delayed, right? So I think we can take a short break, 5 minutes. I'll just stay here in case anyone wants to come and any questions. But when I come back, I will jump some slides and go into some case studies, right? So we'll practically solve and find out how long it takes if it is persistent, if it is non-persistent, how long it takes if it is persistent but not pipeline, how long it takes if it is persistent but pipeline. And once we solve these things, then we'll come back and then we look at other solutions. So these solutions are the protocol improvements. The other solutions are like caching, and then we'll see how caching can help. And then we are going to look at bandwidth, like I can also have bigger pipe, bigger network bandwidth, and then we'll see how they can help. And then we will compare and contrast these solutions so you have a more comprehensive repertoire of solutions at your disposal, because if you are working in the industry, it's not just always one solution fits everything. Different industries have different requirements, restrictions, objectives, right? And facilities and flexibilities. So the idea here is to go through all sorts of options that are available to you, understand them very well, compare and contrast. And that will be the bulk of today's lecture, and I just need 10 minutes to cover the email because I just wanted to show you the main protocols in email. So I think this is a good time to take a 5 minutes break. I'll see you in 5 minutes. Okay, so we are back. We are going to resume our lecture. As I told you, I'll jump some slides and look at some cases, all the cases, non-persistent, persistent pipelining, persistent without pipelining, and then we'll see if we can derive the formula for each one of them, right? So again, I don't want you to memorize these formulas because you will see it will be very difficult for you to judge whether this formula applies to the case study that I give you. It's better to understand why these formulas are correct. So I'll derive with you, I'll be with you. If you have any questions, just let me know. It might sound overwhelming, too many things here. So let's try to understand this quiz. So remember when I say base file, then I'm referring to, sometimes these are just terminologies. I'm referring to index file, right? So this is the HTML file. And it has a size S0, right, base file. And then once you download this file, then you will see that this HTML file is saying there are n objects, right? And each object, for simplicity in this case, each object has the same size, S bits. Now the browser, the client, fetching the page over a link which has a capacity of C bits per second, right? So there's lots of numbers here, C bits per second. So that's the capacity of the line. And the round trip time for this particular client and server is D seconds. Okay. So how long does it take to download the page using non-persistent, okay, and without parallelism, right? So we have just studied the non-persistent. So we know, how much round trip time is involved if you're using TCP and interacting with the TCP. So you have all the information. The question is, which one is correct, right? The answer is B, D for Danny. Okay. So one student is saying the answer is D. Is there any other answer? I'll give you a minute to work on it. And this is not the exam, so there's no problem if you don't get it right. And we are going to go through, we'll derive it. I'll derive it in front of you. So if it helps, you can go to the next page, which gives you an example. Anyone else wants to offer any other or the same one? Did you manage to find the answer? D? D for Danny? Same? D? Okay, so I already have multiple answers. The answer is D. So the correct answer is D. Yes, you got it right. So well done. I'll just mark it so that if you watch the record that you will see the correct answer is D. However, for many students you are still wondering how I got it, so it's important to actually see why this is the answer. So in the next page what I have done is I gave you, the font size is not the best, but this is a small case. So n is equal to 2, so you can trace it, and you'll see that the first TCP connection, 1 round trip time, so this is D second. Then you need 1 round trip time to get the base file, right? So you can see this is base HTML, right? And then you can see to transfer the base, it takes S0 over C, right? So that's the, I mean, it's not free. I mean, it might be a small file, but, you know, depending on the capacity. I've not given you what's the capacity. Capacity may be very low. So it's S0 over C. So we spent D here, S0 over C here. Then we request non-persistent, so one object at a time, right? So you ask for that object and you get that object, good. But at this point, TCP connection is closed, so you have to open another TCP connection. So this is coming from the TCP, right? This is the object download, so it's S over C rather than S0 over C, right? Then you get it, and then for the second object, again, you have to open the TCP connection, then you have the object. So you can see you have to open TCP connection here, right? And you have to open TCP connection here. So there are two objects, two TCP connections, and in the beginning you have another TCP connection, right, for the main base file, right? So for the base file you have one, and then two objects you have two. So you can see you will always have one round trip time, right? That's for the beginning. You have to open the TCP connection. Then you have to get the base file, and then you need TCP connection for all of them, all of the objects. So there has to be ND. So you can see the way it shows you here, it has done some manipulations. So where this 2D coming from? So this 2D is coming from the downloading the base file, right? One is for TCP and one is for the HTTP, 2 round trip time. Right? You agree with that? And then you have S0 over C. So this is actually the transmission time, if you like. Transmission time of the base file. For every object, you have 2D because you know one is TCP and one is HTTP, but here the object size is different than the base size. Base size was S0, here is SC. So this is for every object, right? And you have n object. Do you have any questions how we got this? Okay, very good. So the subsequent ones will be easier. So I took some time because we need to understand how it works. And then I'm changing the quiz only here. Instead of non-persistent, I'm saying that this is persistent, right? So if I switch from HTTP 1.0 to 1.1, and then I say that let's go for persistent, however, we don't want pipelining. Remember, you have two options for persistent, pipelining and non-pipelining. So this is no pipelining, right? So again, I'll give you 1 minute to work it out and tell me what is the correct answer. They look very close, but they are different. You have the answer? E for export. Anyone else agrees with E, disagrees with E, agree with E? We have two agreements. Same, agree? Good. I can see quite a few of you already work it out. You got it right, that's the correct answer. So I'll just mark it here. That's the correct answer. So why this is the correct answer for pipelining? Again, I've given you a very small case so you can trace it, and you can see you need the TCP connection open. I mean, you have to open a TCP connection, but this is persistent, so we are not going to see any more TCP connection related RTT. So the next one is for the base file, right? And this is the time for the base, and then you download one object. So one RTT for one object and one RTT for the second object, right? And then you have the object transmission time here. So you see there is no more TCP here. So this is a much simpler one. And if you look at here, the 2D is because one TCP and one HTTP to get the base file. So this is for the base. Right, and this is the base file transmission time. Right? So the simplification comes from here. It's just D plus S over C. There is no 2D here, so just single D. And that makes a huge difference when you have a big multiplier N. So you can actually go back and work it out. I'm sure that there may be students, but if you have questions, yes.
The D, that's the round trip
Time, yes.
Is that saying that there's a round, like, that's saying like me there's a TCP connection made every object?
Oh, here?
Is that what that implies?
No.
So why is there a TCP? Is that
This is the HTTP. So this D is the HTTP. Does it make sense now?
So before, when it had
Two times. One is for TCP and one is for the object. So this D here is for the object only, for the HTTP related round trip time.
and so the 2D at the front of this one, that's once the connection and once the...
Yeah, you have a TCP, yeah. I'll also annotate that so you remember it. Yeah, it's a good point. So I can go back here. Okay. Right. So how, I mean, here we are just giving you variables so that you can capture any case study. But the case studies will have actual numbers, right, and actual cases. For example, you know, this is the website, you know, and you can see how many objects and things like that. Then you can see trying to find out which formula fits this is more challenging than if you just solve it yourself. But to solve it yourself, you need to understand the timing diagram for pipelining and non-pipelining, and persistent and non-persistent, and that was the focus here. And if you still have questions, just let me know, right? So, oh, did we actually skip? No, I think that was the persistent without pipelining, but I think this will still be valid. This is still valid, but the answer is not E. This is not the correct answer. So I think we skipped one slide. So I just want to, I think it will allow me to undo. No? Okay, I'll find a way to. Yeah, I think what I did, I annotated 3, and it's not 3 we were discussing, remember? Should just delete it. Okay, so we were actually in this quiz, right? Persistent, and the correct answer was here. And we are following this one, remember? N is 2. So this 2D comes from one TCP, one base file. This is the base transmission time, and this is for every object. Right, so D over SC. Did we do it right for this one? Yeah, the answer was D, and there was 2D, and now there is 1D. So that's the difference, right? You don't have a TCP connection set up for every object because this is persistent. This is persistent. Yes. Closing the connection. It's a good question. Is there any time to close the connection? In TCP, when we go to TCP, you'll see there is no time wasted in closing the time. So closing a TCP connection process is different than opening a TCP connection process. Opening a TCP connection process is a 4-way handshake. Fundamentally 3-way handshake. 3-way means you send, the server sends, and then you send. So that's why it's a round trip time. Closing is, I mean, there are good options. You just close it and that's it. I don't care. I closed it. I'm the server. I closed the connection or something.
It doesn't affect the download time.
Yeah, it doesn't affect. The closing doesn't affect. It's the opening. Yeah. But opening and closing will always be there, but don't worry about the time with the closing. Yeah, but that was a good question. Yeah. Right. So inadvertently, we have actually covered both of the quizzes here. But nevertheless, let me ask you, so what is the, if I switch it to pipelining, so this is the difference between the last quiz and this quiz. So before it was not pipelining, but I am pipelining it. So that should be simpler, right? If you look at here, we still have, you know, every object, it's like D plus S over C, but we should be able to simplify it, right, with pipelining. So what is the answer? Yeah, I'm hearing D. D for daddy, D for Danny, whatever. So D is the simpler one, as you can see, but it has 3D. Okay, this is some processing of it's called algebraic processing, and that's why I don't like you memorizing these formulas, because the formulas themselves, without the context and how you derive it, they don't mean much. It doesn't add significantly to your learning experience. What is 3D and things like that? These are just algebraic manipulations. So if you look at here, this is the pipelining, right? This is the pipelining. So you can see you have to open the TCP connection. There is no avoidance of TCP. You have to open the TCP connection once. So you have 1D. Then you have to get the base file. So you need 1D, and you have to get the transmission. You have to experience the transmission time of the base file, which can be very small, right? Then it's pipelining. So its pipelining is here. See, the two objects are requested back to back in a pipeline without waiting for the first object to be downloaded. That makes some difference. What's the difference it makes? As you can see, that you have only a single round trip time for two objects. But if you have to wait for the first object to be downloaded before you request the second one, you will have two round trip time for two objects. And now you have a single round trip time for two objects. If you have 100 objects, still you have one download time for 100 objects, and the savings will come when you scale, right? Yeah.
Is there any substantial increase in the transmission time for the actual request when they're requesting multiple?
You mean the request, the size is very small. Yeah, so we are ignoring them. But we are not ignoring this one, the base file, because sometimes the HTML code is large, especially if you have a very complex website. HTML code is complex. So it takes a certain time. That's why I didn't ignore it. But the request is, you see, is just few bytes. So I skipped those slides. You can see the format. It's just a header and some ASCII characters. But yes, if you are pedantic, like if you want to capture it, capture everything in your formula, then yeah, you need to make it more complicated. But we'll ignore them. Yeah, it's a good question. Any other questions? Do you see? So we have done 3 quizzes in succession. Started with non-persistent, then made it a little bit more complicated, persistent, right, without pipelining, and then we made it more complicated but better by using pipelining. And you have seen the answers, they have changed. So I think I have to mark the answers before I forget. So what was the correct answer? It's D, right? So in this case, you can see 1D, right, 2D, and then 3D, right? So that's why it has 3 Ds. 3 Ds, the download time of that one, and for all the objects transmission time. So these are the transmission time, right? Is there any questions? Okay. One thing we have not done, though, is the parallel, right? Because the parallel creates lots of overhead. But if you do parallel, you should be able to reduce, right, the download time further, assuming that this parallelism will not overload the server so much that the server delay becomes a new variable, right? Okay, so far so good. I think we can move on. I'm now going back because we jumped, and I wanted to show you other solutions, right? Okay, so what we have done so far is improving the protocol, right? The interaction with the TCP. And we can see we can bring substantial improvements in terms of the user experience by implementing these changes in the protocol. The way the TCP connection will be used by the HTTP, right? Now we are going to see, is there any other ways to improve, right? And you will see that caching is a very interesting solution. Caching is used in computer networking in many different layers and in many different applications. So here we are going to see how caching is used in HTTP to improve the performance. So you request something, right? And you always request from this server, and this server will use a cache, right? So if the object is in the cache, it will actually not go to the origin server. So this is the origin server. That's where actually the objects are. And when you download the base file will say that the object is here. And the object is here because your HTML code gives you the URL of the original server. However, you are trying to get it from a proxy web server, which is a cache. And your institution, your company, would like to have a web proxy server and configure all the web browsers in the company, in the organization, to point to the proxy server as the first point of call. So when the request actually goes to the proxy server first. If it finds it in the cache, the object, it will not go to the origin server, and that will bring significant savings because of the distance and because of the bandwidth. Because within the organization, you have high-speed local area networks, such as this room. We have gigabit per second Ethernet. So we have cabling in this campus. So all the access points, Wi-Fi access points are connected via gigabits per second Ethernet in the backbone. But once our traffic goes out from your home or from your small flower shop, for example, you can have a gigabit per second Ethernet in your flower shop. It's very cheap. But the internet access is very expensive. You might have only 54 megabits per second NBN connection, for example, right? Or you might have a 20 megabits per second leased line, or maybe just 1 megabit per second leased line from one office in a different state to the headquarter, for example. So all the traffic from that office to the headquarter, they go through the secured, but it's a narrow bandwidth. So that's where the savings come in. So if you have to go out to go to the origin, this is where the problem is. This is the internet, but this is a local network. I will show you another picture, and then I will go straight into the case study, and we'll start again. As you can see, there are numbers, there are case studies, so I have to go a bit slow so you understand it, and I'll derive it with you, because it's important that you get it right, but I'll just use these pictures straight away. So what do we see in this picture? Right. So this is a very typical scenario abstracted to this small case study. So this is your company or organization. This is a local. And I was telling you about the gigabit per second Ethernet. So this is the gigabit per second Ethernet. As you can see, so all these machines, they are connected through this gigabit per second switch and router. So the communication here is very fast. We are talking about only microsecond delay within the local area network, because the bandwidth is not a problem and the distance is not a problem, right? The problem is if you try to get an object, so the scenario is like this. So they have a browser. So people are behind these browsers, right? And these browsers, you are watching and downloading the HTML file, and you're clicking all the time, and lots of objects are requested from the web, right? And all these objects needs to come to your organization so it can be displayed on these browsers, right? Okay, so a lot of traffic will come to this organization, and these are the origin servers in the internet, maybe some in the US, some in another state, right? So what are the numbers? Access link, 1.54 megabits per second. Which one is the access link? This is the access link. So this is your internet connection, right? This is the access link. This is 1.54 megabits per second. RTT from institutional router, so this is your institutional router, to the origin server is 2 seconds. So this would take you 2 seconds. This would take you 2 seconds. Okay, so these are just assumptions. These are just some numbers. Don't worry, it may be far away. So for simplicity, any origin server in the internet, you have to experience a delay of 2 seconds. Each object in the web browser here is 100 kilobits, K, don't forget the K, kilobits. So 100 times 1,000 bits, right? For simplicity, different objects have different sizes. But here, for simplicity, it's 100K, right? What is the average request rate from the browsers to origin servers? Is 15 per second. So if you aggregate, so they are creating requests. So it's 15 object requests per second. So the aggregate is 15 per second. Okay? Not to, let's call it from. So if you look at the data rate, so you are generating 15 object requests, right? And each object is 100 times 1,000 bits, right? So the total amount of requests that are coming from these browsers for downloading traffic into your organization is, you have to multiply these things, right? So how do I get 1.5 megabit per second load? Is there are 15 per second, right? And each one is 100K. So if you multiply these two, you will see it's 1.5 megabits per second. So these browsers are creating, on average, it fluctuates, but on average, it's creating 1.5 megabit per second traffic load into this organization, right? Due to web. So this is the web traffic analysis. You can collect these statistics. These days they are collected automatically. And whoever is designing and analyzing the network, they have at their fingertip this kind of statistics. It's not a problem, right? 1.5. Okay, we got another number. We have lots of numbers, so be patient. What I mean by utilization, why is it 0.0015? So LAN utilization, so local area network. LAN means local area network here. This local area network has a capacity of 1 gigabits per second. It's a very high-speed local area network, right? And we just want to show that this LAN is not overloaded, because if the LAN is overloaded, then this becomes the bottleneck for your experience, right? So how did I get, so you see the amount of traffic that you will generate, the web traffic is 1.5 megabits per second. So it's 1.5 times 10 to power 6, right? Megabit per second divided by 1 gigabit per second. So if you do this maths, then you see it's 0.0015 LAN utilization. LAN utilization, the maximum utilization is 1, right? So you generate 1 gigabit per second traffic. The LAN is hugely congested, and then you will see nothing is getting through your LAN. So LAN is not overloaded, it's lightly loaded. This is a typical scenario. That's why we go for 1 gigabit per second, 10 gigabit per second, 100 gigabit per second in big organizations. Access link utilization is 0.97. Why? Why we say it's 0.97? Remember the load here? The capacity is 1.54 megabits per second, but your traffic load is 1.5, right? I'm going to use my calculator. I thought it was right, just double checking. So if I divide 1.5 by 1.54 is 0.97, I'm correct. 1.5, 1.54. So this traffic, 1.5 megabit per second web traffic, is not congesting the local area network. Local area network utilization is 0.0015, but the problem is the access link, which is the expensive link, that becomes congested, 0.97 the utilization. What's the other name for utilization for this access link? Do you remember from week 1, we talked about queuing theory? There was a terminology. Traffic intensity, exactly. You have better memories than I have. Okay, good, 0.97. What does it mean? So yeah, you have a good memory of your terminology, but do you also remember this? So this is traffic intensity of 1.0. So this is your delay in the y-axis. And so that's your delay. And in the x-axis, this is your traffic intensity, right? Or in this case, now we are here. I can use this terminology, utilization, right? Traffic intensity. Do you remember this curve? How does this curve look like? Who remembers it? Yes, good. I saw someone using hand gesture, so let me repeat the hand gesture. That's what he was trying to show me. So the delay grows exponentially, infinitely, as you increase the utilization of the traffic intensity on your link. This is the queuing theory, right? And we have seen why this is true in lecture 1, right in lecture 1, because the packets wait behind the queue before they can get serviced. So if the traffic intensity is very high, then the queue will build up and your average delay will go exponentially higher. And we had also an animator. You can play that animator to see by playing the access link and the packet arrival rate traffic intensity, and you can see how the packets are getting dropped and the delay is increasing. Why I'm mentioning all of these things here? Okay, so The reason I'm mentioning all of these things here because I want to justify that the delay in the access link will be huge, orders of magnitude higher than the delay in the LAN, right? It will be even higher than the internet delay, which is 2 seconds. And LAN delay, this is microsecond only. So LAN is nothing, internet delay is something, but this access link delay is the killer, right? And this is like, well, for every organization this is not the case, but we can kind of say this is true. So you can see end-to-end delay is dominated by the access link delay. So you want to solve the problem. So one solution, get a faster access link, pay for it, right? You have money, right? You're the CEO, you say nothing is working in your organization, you know, how much do you need? And they say, I need another, you know, $500,000 in lease cost to connect my site to the headquarters. CEO says, okay, go for it, $500,000. Okay, you say that, okay, forget about 1.54. I can get 154. CEO has just approved it, right? And you can say the minutes becomes milliseconds, right? And everyone is happy. Good. What is the bottleneck now? Who is the bottleneck now? RTT in the internet is the bottleneck, 2 seconds. Because minutes gone, you threw money at it, right? So your bottleneck now is the internet, 2 seconds. You can't do anything about it, just buying bigger pipe because the origin servers are very far and you can't beat that 2 seconds with the access link speed, okay? So you solved some problem, but now you are stuck with this 2 second thing. And the link access speed is not solving this problem. So now we see where the web cache comes in, how web cache can help. Now we are saying this router, you just implement an HTTP proxy web server which will cache all the popular objects, right? And how can it help? Can we now address this 2 second internet delay? The answer is yes, but it's a bit complicated. Cache doesn't mean that if I request it, it will be in the cache. Cache means that there will be a high probability that it will be in the cache, right? So you will need another variable into our discussion. That variable is called hit ratio, right? So if you are playing with cache, you need the hit rate. Hit rate in this case is 40%, and the miss rate is 60%, right? So there's a 0.4 probability you will find it in the cache, 1 minus 0.4 probability you will not find it in the cache. If you find it in the cache, then it's in the local area, you know, microsecond delay. If you do not find it in the cache, it will go to the 2 second delay, right? And we are saying that I'm not going to throw any money here. This time I asked the CEO for some cash. Let's not use cash. Cash, both are cash. Ask for a little bit of money, funding to upgrade our router to have some web proxy. That's not expensive, right? You just need to buy. Instead of $500,000, you just ask for a few thousand. And you get it because it's few thousand, it's immediate. You deploy it, so you do not upgrade your 1.544. So what's the outcome? If you do all these calculations, you will see the outcome is 1.2 seconds approximately. These are approximate, okay? Don't worry, where do I get this 0. So this 0.4 is the hit one, 0.6 is the miss one, 2 is the internet, and 0.01 is the delay here. So the bottom line, the story here is that we didn't spend for the access link upgrade, but we spent for the cache. Cost was significantly lower, and the performance is better than 2 seconds. Right? 2 seconds was the bottleneck, and we were able to address that bottleneck even without spending any money for the upgrade of the access link to the internet. Right? So that's the power of caching. Okay. Any questions so far? Yes?
Why applications only used for institutions? Why haven't you used it like public?
Why they are institutional, why they are not public. If it's within your institution, then you get the microsecond delay within your. If you have to go to the public, you have to go out the access link, and that's where the bottleneck is.
So why aren't there caches like as part of the internet to reduce that?
Why we have caches in the internet? Okay, so yeah, it's actually it's a good question. So when we study CDN, content distribution networks such as Akamai, you know, so they face this problem. So where to put the replicator? So cache is cache. The other one is not cache. It's called replication, right? So what is cache and what is replication? So cache is like is not the original object, right? You are just caching it, right? You are caching it. The real object is in the origin server. Origin server makes decision about when to change the object, and in the cache you wouldn't know that, and it may be stale. So one of the drawback of cache is that there is a probability that you are not you are getting the stale content, right? Especially for dynamic content, highly dynamic contents. So replication is the responsibility of the original server to replicate the originality closer to the user. So if I update in one of my origin servers, I have to update in all of my origin servers. So origin servers, they deploy very close to the user. So instead of having one origin server in the internet in the US or somewhere in the UK, they would have 200,000 origin servers distributed throughout the world, depending on the population and the geographic locations, right? So when you request from, you can go to the origin server all the way without worrying about the cache, yet the delay is not significant. So that's called the replication. Now, you say how far they can push this replication to, I mean, if they keep it in the public, even if it's close to you, it has to go through your access link. And that's where there will be some delay. So that's why you still need the cache within your organization, so you can even save further. Does it answer your question? Yeah, good. So if you don't have any further, I want you to go over these slides because, again, I will not make any secret. I will ask questions from here, right? Cache, persistent, non-persistent. Yeah, there's a question. Can you speak up? Web cache? Oh, these days? Oh, yeah. Caching is used everywhere. You wouldn't know, right? It's a decision of the organization to use cache or not. But there are some protocols for caching. So they use TTL, time to live. So when you cache, the origin server tells you do not cache it more than 1 day or something like that. For example, I'm a newspaper. I update my newspaper every 24